Alrighty, in this video, let's go over the concepts of hypothesis testing. Hypothesis testing is another way that we can take a sample and use that sample to make an inference or a statement about a population. In the same sense of how we use samples to create confidence intervals, we're going to be using samples to do hypothesis testing. And at the end of the day, hypothesis testing is just checking to see if a population parameter, whether it be a proportion or a mean, if it's significantly different than what we're proposing, okay? So in this video, guys, we're just going to go over the main concepts of hypothesis testing on a high level, not really get into formulas, and then in the subsequent videos after this, we'll get into some specific formulas for different cases, all right? So let's kick things off with the different types of hypotheses. So when you're dealing with hypothesis tests, there will always be two types of hypotheses. You will always have a null hypothesis, which is denoted with H with the subscript 0. Okay, that's a null hypothesis. The null hypothesis always states that whatever your population parameter is, and once again, it could be either a proportion or a mean, just like with confidence intervals. The null hypothesis says that your population parameter value always remains unchanged. So whenever we deal with a null hypothesis, it will always include the inequality equals to. So whenever we deal with hypotheses, we always have to specify an inequality. So for the null hypothesis, it will always be an equals to. The second type of hypothesis that we'll always have is called an alternative hypothesis. And a lot of times this is denoted HA, but sometimes you'll see it denoted with the H with the subscript 1. It just means alternative hypothesis. This states that the population parameter has changed. And a parameter can change in different ways, right? Sometimes we want to test to see if the parameter has increased or is it more than. So that corresponds to an inequality of a greater than. Sometimes we want to see if a parameter value, mean or proportion, has reduced or become less than. So that's the less than. Or sometimes we want to just see if the parameter is different. So different is that case where you are both greater than and less than a specified value. In that case, we use the not equals to. So the equals to with the slash through it is called not equals to. Okay, so let's get into an example where we practice writing out these hypotheses. Suppose we wanted to perform a hypothesis test to determine if the population proportion of people that voted for a specific candidate is more than 30%. Write the null and alternative hypotheses. Okay, so we want to check to see if this population proportion, which we don't know, is more than 30%. Okay, so the parameter that we're going to use for this particular example is P. Remember, P means, let's come over here, P is your population proportion. Okay, so we want to, let's first of all, let's write the null hypothesis. So the null hypothesis, as I tell you, it's always an equals to. So we're testing if the population proportion is equal to, the null hypothesis saying that the population proportion remains unchanged. AKA the population proportion P is equal to 30%, which we always write as a decimal. The null hypothesis will always have an equals to. The alternative hypothesis is where things get interesting. This is where it comes into place that we're trying to test or see if the proportion is more than 30%. So the alternative hypothesis is P greater than that same 0.30. So this is your set of hypotheses for this particular hypothesis test. Every single hypothesis test will include a null hypothesis and an alternative hypothesis. Let's look at another example. Consider the problem where we want to test if the proportion of people who voted for a specific candidate has changed from the value of 25% that was reported earlier in the polling cycle. Okay? So once again, we're going to have two hypotheses, the null and the alternative. Well, the null, we're still talking about population proportion. It's still going to be P equals what? P equals 25%, which we write as a 0.25. The alternative hypothesis saying, listen, we're trying to check and see if this proportion has changed. So changed or different or differs, that is your key word to indicate that we are going to test, as far as the alternative hypothesis, if the proportion is not equals to 0.25. Okay? All right. So once again, guys, really quickly, if they talk about less than, obviously that's going to correspond to less than. More than obviously means a greater than. If it says anything like changed or different, okay, those are your key words that you're dealing with a not equals to case for your alternative hypothesis. But the null hypothesis will always be an equals to. All right, just a few quick little tidbits here. We note that we can only test or prove the alternative hypothesis. And this is, this is similar to a court scenario. What I mean by this is oftentimes when we introduce the concept of hypothesis testing, we make the analogy of the null hypothesis being similar to, let's say you get arrested, unfortunately, right? What do they say when you get arrested? You are innocent until proven guilty, right? So what that means is that no one, or the prosecutor or the courtroom, doesn't have to prove your innocence, right? Because you are given that. That is something that you don't have to prove. What they have to prove is if you're guilty or not. And that's what it is. So the null hypothesis acts like your innocence. You are given innocence. The H null is given. You do not, that's not what you're proving. What we're trying to prove is whether or not the alternative, which is that guilty conviction, whether or not that's true or not. So you'll see throughout this lecture, we'll make that connection between hypothesis testing and, let's say, the legal system. Okay, so as I said, we can only really prove or disprove the alternative hypothesis. So how do we determine if the alternative hypothesis is correct or not? Well, what we're going to do is, as I said, similar to confidence intervals, we collect samples, right? And so since we're using samples, you guessed it, the central limit theorem has to be invoked. Okay? Once the central limit theorem is satisfied, now we have a distribution, a sampling distribution, right? And we calculate a test statistic. Okay? So a test statistic is a representation of the data that you collected, the samples that you collected. A test statistic will be either a z-score or a t-score. More on this in future videos, but really quickly, if we're doing proportion stuff, it's going to be a z-score. If we're dealing with means, remember we deal with the t-distribution for means. And so what we do is we compare this test statistic to the distribution of our null hypothesis, right? And so, as I mentioned here, the formula for the test statistic will vary depending on what you're testing. And so as I said, as we go through subsequent videos after this one, you'll see the different test statistic formulas. Well, basically, we have this test statistic, okay? And we're going to calculate something called a p-value from this test statistic. What is the p-value? The p-value is the probability that we get the observed results from our samples, or something more extreme, assuming that the null hypothesis is true. Okay? So another way of looking at this is saying that the p-value tells you the likelihood that your data can occur, the samples that you have occurred, given that the null hypothesis is true. So it's saying how likely is it that I am to get this sample that I got, assuming that the null hypothesis is true. Okay? Well, this p-value is that probability, that likelihood, okay? And so what does a higher, so p-value will go between 0 and 1. So let's make note of that real quick. So p-values are probabilities, they go between 0 and 1. So you'll never have a p-value less than 0 or a p-value greater than 1. Keep that in mind. But what does the actual p-value tell us? So a higher p-value, right, indicates that our data, remember the p-value is a probability, it means that our data is more likely to occur assuming that the null hypothesis is correct. So what that means is that basically it's saying that, yeah, we're pretty sure that the null hypothesis is giving us the correct information here. So in this case where your p-value is large enough, we should not reject the null hypothesis. Okay? We should not reject the null hypothesis whenever our p-value is large. If our p-value is small, what that means is that it is very unlikely for us to obtain this sample given that the null hypothesis is correct. So that means either we got really lucky, or our null hypothesis is wrong. Well, in stats, we don't believe in being super lucky. So that means that, yes, our null hypothesis is incorrect. Therefore, we should reject the null hypothesis. And we should go ahead and say that, yes, the alternative is the correct hypothesis. Okay? So there's two scenarios that can happen. With the high p-value, what you do is you do not reject the null hypothesis. So simply you're saying, listen, I don't have enough evidence to say my null hypothesis is not true. Or if you have a really small p-value, you say, hey, I have enough evidence now, more on this in a second, that we should reject the null hypothesis. I know this seems like a lot right now, but trust me, you guys will get a lot of practice of this over the next few videos and homework problems. So, as I said, the p-value is a probability that we get our data, our test statistic, or something more extreme. Meaning, how do we know? If you remember how we calculate probabilities, right? With the normal calculator or the t-calculator, we needed bounds, right? And so this next section, I want to go over how do we know kind of which way we should shade our normal distribution to calculate the p-value. Well, here we go. I'm glad you asked. So I'm just going to go over the different cases, okay? There's nothing in particular about how I number these cases. So let's talk about case one. So case one is the case where, so remember, central limit theorem says we have an approximately normal distribution. And let's say that our test statistic was, I don't know, somewhere over here. So this is our test statistic, okay? And let's say our alternative hypothesis for this case one, let's say it's the case where, I'm going to go back to proportions, where the proportion is less than some value. Let's say, I don't know, some number, which I'll call 0.30, let's say. Well, what this means is that your alternative hypothesis tells you which extreme you should calculate. Meaning, you see how the p-value is less than 0.30 or less than anything? Anytime we have a less than, this indicates that we are calculating what's called a left-tailed test. And I just sounded really country right there. So this is a left-tailed test. The reason why we call it a left-tailed test, because since our HA, our alternative hypothesis, is less than, it means we are shading to the left. Okay? So all of this red shaded area, that is going to be our p-value. Okay? So to know which way to shade, you look at your alternative hypothesis and you just look at the inequality. If it's pointing to the left, it's a left-tailed test. If it's pointing to the right, let's talk about case two. Let's say in this case, the alternative hypothesis was, let's do the population mean. Mu, let's say mu is greater than, I don't know, 15. All right, let's say we just had that. Well, what does that scenario look like? Once again, normal distribution. Let's say our test statistic, and our test statistic could be anywhere. I can draw this anywhere. I'm just being arbitrary here. But let's say our test statistic is somewhere here. So test statistic that we calculated from our data. And so since our HA, our alternative hypothesis, is pointing to the right, that means we're shading to the right of that test statistic. So all of that area to the right of the test statistic, that is the p-value. And for that reason, we call this a right-tailed test. A right-tailed test. Okay, let me actually write that a little neater. Right-tailed test, okay? So the moral of the story, guys, is check your HA. And the third and final case is what happens if we have that not equals to scenario. So let's say our HA is, let's go back to population proportions. Let's say we're testing if our proportion is not equal to 50%. Well, what in the world do we do with that? Well, what this scenario looks like is that we're going to have not one test statistic, but two. And the only difference between them is that one is a negative. So this is our negative test statistic. And one is a positive, and it's equal distance from the center there. So this is the positive version of the test statistic. And so what we're going to do is we shade area in both tails to the left of the negative test statistic and right of the positive test statistic. And that combined area, that is the p-value. Okay? So it's going to, often what we do is we calculate one of the tails and then we just multiply it by 2 because they're the same due to symmetry. And so for that reason, we call this a two-tailed test. Okay? All right, so that's how we calculate, or at least those are the different cases on how you calculate your p-value. Okay? So moving along here. Once we calculate our p-value, right, the question becomes, how do I know if my p-value is big enough so that I can say, hey, you know what, we probably shouldn't reject the null hypothesis because it's pretty likely that we get this data set. Or how do I know if it's small enough so that we should reject the null hypothesis? Well, to make a decision concerning whether or not the alternative hypothesis is correct, we compare the p-value to a number that's called the level of significance. And the symbol for that is the Greek letter alpha. Okay? So to make a decision, what we do is we compare the p-value to this Greek letter alpha, which is called the level of significance. What is the level of significance? Well, basically the level of significance is the probability of an error. Okay? Specifically, it's called a type 1 error. We can, if you have questions about that, just shoot me an email. But basically, just know that the level of significance is an error probability. The level of significance, right? It does not depend on your sample size. Okay, this alpha has nothing to do with your sample size, and it's typically chosen before you start your experiment as well. Okay. So, and it's given, so as far as us in this course, alpha will be given to us in the problem, but if it's not, the most typical alpha, the most used alpha is an alpha value of 5%, 0.05. Okay? So that's typically what we use. Sometimes you'll see an alpha of 0.01. Okay? And, but generally they should tell you what the alpha is in the problem. Okay, so what do we do? So we calculate the p-value using the steps I showed you before. And it turns out that if your p-value is less than your alpha, your specified alpha, then you should reject the null hypothesis. Memorize this, folks. If your p-value is less than alpha, we reject the null hypothesis. Okay? More on what this means in just a second. On the other hand, if our p-value is greater than alpha, then we should fail to reject the null hypothesis. Okay? Or sometimes they'll write, do not reject the null hypothesis. It means the same thing. Okay? So those are the cases, folks. Really easy comparison for us. If the p-value is less than alpha, reject the null hypothesis. Okay? If the p-value is greater than alpha, we do not reject the null hypothesis. And you may notice, so when the p-value is greater than alpha, you notice how we say we fail to reject the null hypothesis as opposed to accept the null hypothesis? And that is very intentional. That is because, once again, let's go back to the legal system. Whenever somebody is innocent, right? So fail to reject null hypothesis. Remember, the null hypothesis is innocence. If we fail to reject the person's innocence, that means that they're innocent. Well, once again, every person that walks out the courtroom innocent, have they necessarily been proven innocent? That's not true, right? What that means is that there was just not enough evidence to prove that they were guilty. So we use that language very intentional here in stats, okay? Because we fail to reject the null hypothesis indicates that We don't prove if you're innocent or not, but we just say that we don't have enough evidence to say that you're guilty. All right. So I just wanted to make a little sidebar about that. And then also too, guys, hypothesis tests and confidence intervals are often reported together. Just for the fact of, because let's say that our p-value is really close to alpha, sometimes it's really good just to look at the confidence interval for your parameter, just because it gives you a good idea of what's the lowest and highest, potential values for your value. But also too, they're related in the fact that this alpha, this level of significance, it's 1 minus your confidence level. So for instance, if you're doing this and it's related to a 95% confidence interval, it means that alpha is 5%, right? So alpha is the percent that you're not confident. That's why it's the probability of an error. I hope that makes a little bit of sense. Okay, lastly, folks, the interpretation. So we've done all this. We've decided we've either reject the null hypothesis or do not reject the null hypothesis. What in the world does that mean in the context of our problem? Well, it means this, guys. If we reject the null hypothesis, and so I want to remind you, this is the case where the p-value is less than the level of significance. Okay, so in order to reject the null hypothesis, this indicates that we have significant evidence that the null hypothesis is incorrect. Therefore, we can confirm that the alternative hypothesis is correct. So in this case, when your p-value was smaller than your alpha, it means that it is very unlikely, if the null hypothesis is true, that we collect the data that we collected. So that means that the null hypothesis distribution is incorrect. Therefore, we reject the null hypothesis and we say that the alternative is the correct hypothesis. Okay? Also, go back to, once again, the legal system. If we reject the null hypothesis, right? Remember, null hypothesis, equate that to being innocent. If we reject someone's innocence, we're saying that they are guilty. Can we just walk around and say that people are guilty? No, we have to have significant evidence in order to say that someone is guilty, that they're not innocent, right? So that's what I want you guys to know. If you reject the null hypothesis, know that that indicates that we have significant evidence. For that same reason, we say that the result in this case is statistically significant because we had to have enough evidence. On the other hand, and we kind of touched on this a few minutes ago, if we fail to reject the null hypothesis, this indicates that we do not have enough evidence to say that the null hypothesis is incorrect. Okay? This case is not statistically significant. So an easy way I want you guys to remember this is that, think about this keyword here, fail. Anytime you fail in anything, what does that mean? That means not enough. When you fail a test, that means not enough points on your test that you scored. When you fail a driving test, that means you don't have enough skill. When you fail in life, well, let me not go there. But anyways, listen, guys, fail means there is not enough of something. And so in this case of hypothesis testing, it means there is not enough evidence to say that the null hypothesis is incorrect. Okay, so I know that was a bit of a trip down conceptual lane, but I wanted to go over the nuts and bolts of the hypothesis test. In subsequent videos, guys, we're going to get down to how we actually calculate our test statistic and get that p-value, and so we can do the full steps. I look forward to seeing you guys in the next video.